This is the second video for week number 8. So in this video, we are going to look at what we call the Question Criterion. Okay, we will define what we mean by a Cauchy sequence and then list a few, some of its properties. So let's begin with this definition here. So if you have a sequence xn of real numbers, then we say that that sequence is a Cauchy sequence. Okay, we call a sequence of real numbers a Cauchy sequence if for any given epsilon bigger than 0, you will always get a natural number capital N epsilon, which depends on epsilon, such that the distance between xm and xn will be less than epsilon, provided both m and n are bigger or equal to capital N epsilon. So we'll say that xn is a Cauchy sequence if for every epsilon bigger than 0, you'll get a natural number n epsilon. Okay, this natural number depends on the given epsilon, right? Such that if both m and n are bigger than that natural number, right, then the distance between xm and xn is less than epsilon. So a sequence of real numbers which has that property is what we call a Cauchy sequence. Now, when does a given sequence fail to be a Cauchy sequence? If I give you a sequence xn, what does it mean to say that xn is not a Cauchy sequence? So you see, if it's a Cauchy sequence, then for every epsilon bigger than 0, you will get a natural number n that depends on epsilon, such that this distance, the distance between xm and xn, is less than epsilon for all m and n bigger than that capital N epsilon. Now we will say that xn is not a Cauchy sequence if this condition fails. If that condition fails. Now, for this condition to fail, it means that there is at least one epsilon 0. You will find at least one epsilon 0 bigger than 0, right? You will find at least one epsilon 0 bigger than 0, such that for every natural number capital N that you pick, for every natural number capital N that you pick, we can call it capital N epsilon, right? Such that for every capital number n that you pick, right, there will always be a natural number. There will always be natural numbers m and n bigger than that natural number, such that the distance between xm and xn is bigger or equal to epsilon 0. Okay, all right. So for every natural number n, you will always get two natural numbers m and small n bigger than that natural number. For every natural number capital N that you pick, you will get two natural numbers small m and small n bigger than that natural number, such that the distance between xm and xn will be bigger or equal to epsilon 0. Okay, so that means that for this epsilon 0, this condition will fail. This condition will not work for epsilon 0. So if that happens, then we say that the sequence xn is not a Cauchy sequence. So let's look at our first example. The first example is the sequence xn equal to 1 over n, and we claim that this is a Cauchy sequence, all right? So let's try to show that this is a Cauchy sequence, all right? So what do we need to do? What we need to do is the following. Given n epsilon bigger than 0, we want to find a natural number n that depends on epsilon, such that whenever small m and small n are bigger than capital N epsilon, right, then the distance between xn and xm is less than epsilon. but in this case, xn is 1 over n, xn is 1 over n, and xm is 1 over m. So we want to find a natural number capital N epsilon, so that when small m and small n are bigger or equal to capital N epsilon, then the distance between 1 over n and 1 over m is less than epsilon. Now, so here we use the triangle inequality, okay? So write down the distance between 1 over n and 1 over m using the triangle inequality that is less or equal to 1 over n plus 1 over m, okay? So this inequality comes from the triangle inequality. Now, we know that given epsilon bigger than 0, the Archimedean property ensures the existence of a natural number n epsilon such that 1 over n epsilon is less than epsilon over 2. That we get from the Archimedean property. So given epsilon, right, bigger than 0, there will be a natural number, call it n epsilon, such that 1 over n epsilon, right, is less than epsilon over 2. Okay, just application of the Archimedean property, right? So if small n and small m are bigger than n epsilon, right, then 1 over m, 1 over small m, okay, and 1 over small n, and 1 over small n, all right, this is n, and 1 over small n, okay, both this will be less than 1 over n epsilon, okay. So if small m and small n are bigger than n epsilon, then 1 over m and 1 over n, both this will be less than 1 over n epsilon, okay? So that means that this will be less than 1 over n epsilon, capital N epsilon. This will be less than 1 over capital N epsilon, and so this will be less than epsilon over 2. This will be epsilon over 2, less than epsilon over 2. So the whole thing will be less than epsilon over 2 plus epsilon over 2, which is equal to epsilon, okay? So that shows you that the sequence 1 over n is a Koch sequence. So the next example, example 2, we want to show that the sequence defined by 1 plus minus 1 to the power n is not a Koch sequence. So that means that we need to find some epsilon bigger than 0, okay? We want to find some epsilon bigger than 0, right? Such that for any natural number n, okay, for n natural number n, okay, you will find m, natural numbers m and n, okay, bigger than n, all right, bigger or equal to n, such that the distance between xm and xn and xn, okay, would be bigger or equal to epsilon 0. And that's what we want to do, all right? So this is your xn, all right? 1 plus minus 1 to the power n. Now let n be any natural number, right? Then n, which is small n, let small n be 2 times capital N, okay? That will for sure be bigger than n, all right? 2n is bigger than n. And then let m be 2 capital N plus 1, which is also bigger than n, right? So we simply want to have this is an even number, and that is an odd number. So with this n, small n, and with that small m, we see that both m and n are bigger than capital N, right? And xn, okay? Xn will give you 2, and xm will give you 0. So if you put here xn will be 1 plus minus 1 to the power 2n. 2n here, it will be even, so this will be 1. So 1 plus 1 will give you 2. And if this power is odd, then this will be minus 1 plus 1 will give you 0. So xn will be 2 and xm will be 0. Now, if we choose our epsilon 0 to be 1, we see that xn minus xm will be equal to 2, right? And that 2 is bigger than epsilon bigger than 0. And therefore, we conclude that this is not a Cauchy sequence. Okay? So what we have done is that for every natural number, n, okay, we have got two natural numbers, small n and small m, which are bigger than that natural number, and that the distance between xn and xm is bigger than epsilon 0. Remember, we have set our epsilon 0 to be 1. So the conclusion is that this is not a Cauchy sequence. Okay. So let's look at this lemma, which says that every convergent sequence of real numbers is a Cauchy sequence. So assume that xn converges to x and let epsilon bigger than 0 be given. Then there exists a natural number n epsilon such that if small n is bigger or equal to n epsilon, then the distance between xn and x will be less than epsilon over 2. Now, if small m and capital N are bigger or equal to n epsilon, then the distance between xn and xm can be written as the magnitude of xn minus x plus x minus xm, and this is less or equal to the distance between xn and x plus the distance between xm and x. And this is less than epsilon over 2. This is less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And so that shows that xn is a Cauchy sequence. Let's look at this lemma here, which says that every Cauchy sequence of real numbers is bounded. So if I give you a Cauchy sequence of real numbers, then that sequence must be bounded. Okay, so to show that that is true, let's assume that xn is a Cauchy sequence of real numbers, and then consider a fixed epsilon bigger than 0, a fixed epsilon bigger than 0, say epsilon equal to 1. You can set epsilon to be equal to 2, 3, or 4, so long as it's bigger than 0, it doesn't matter. For us, we are going to fix epsilon to be equal to 1. Then, since xn is a Cauchy sequence, there exists a natural number n, such that if small m and small n are bigger or equal to that n, then the distance between xn and xm is less than 1. Okay. In particular, for n bigger or equal to capital N, we see that the difference between the magnitude of x small n and x capital N will be less or equal to the distance between xn and x capital N, and we already know that this is less than 1, right? So if you get this one and take it to the right, you end up with that, with the fact that if n is smaller, or if n is bigger or equal to capital N, then the magnitude of xn is less or equal to 1 plus the magnitude of capital Xn. But this is only true if small n is bigger or equal to capital N. So we need to take care of the magnitude of x1, x2 up to xn minus 1. So let m be the maximum of the magnitude of x1, x2, xn minus 1, and the magnitude of x capital N plus 1. So you simply let m to be the maximum of this. Then, if you set m to be the maximum of that, then you see that m is bigger or equal to the magnitude of xn for all natural numbers n, and then that tells you that that the sequence xn is bounded.